Welcome to Pavinar's, Webinars for the Pavement Community. My name is Andrew Bram, and today we'll talk about high-float asphalt emulsions. We're going to begin with a very brief overview of asphalt emulsions. What is an asphalt emulsion? How do we use asphalt emulsions? And then how can you find out more about asphalt emulsions in general? And then we'll transition specifically to high-float asphalt emulsions. What are they? Why do they exist? And where are they used? We'll then start digging into literature and talk about how high-float asphalt emulsions are a gel-like structure. And we'll cover some papers that discussed recovery methods and how to characterize the high-float asphalt emulsion residue. And then finally, we'll talk about high-float asphalt emulsions in research, how they're used in surface applications, how they're used in structural applications, and then how they're represented in tomorrow's asphalt emulsion specifications. So let's start out with what is an asphalt emulsion. Here's a small pictogram of an asphalt emulsion, but an asphalt emulsion is small particles of asphalt binder suspended in water. The asphalt binder cannot be dissolved or mixed into the water, and the asphalt binder is suspended in the water with the help of emulsifiers. And you can see in a typical asphalt emulsion, there's approximately 66% asphalt binder, approximately 33% water, and around 0.3 to 3% emulsifier. Now there are several different types of asphalt emulsion. So we have a nomenclature established. We have 4 setting speeds: a rapid, a quick, a medium, and a slow setting speed. We have 3 particle charges: a negative particle charge, which is anionic, which is not represented by any letter, it's simply a space; a positive particle charge, which is cationic, which is represented by a C; and neutral or non-ionic asphalt emulsions. HF stands for high float. -1 is low viscosity. -2 is high viscosity. You have a small h and a small s, which stands for hard and solvent. A capital P stands for polymer. So all of these letters and numbers can be combined in order to name our asphalt emulsions. So for example, a CRS-1P is a cationic, rapid set, low viscosity, polymer modified asphalt emulsion. And HFMS-2S is a high float, anionic, medium set, high viscosity solvent asphalt emulsion. So this is very convenient to have these letters and numbers to very quickly define what asphalt emulsion we're talking about. Now asphalt emulsions can be used in many different ways. One way is with surface treatments, and this is where either an asphalt emulsion is sprayed on a surface, such as fog seal, chip seal, and scrub seals. And you can see that fog seals also have rejuvenating agents as a possibility, or they can be mixed with fine aggregate, and then you get a slurry seal or microsurfacing. And you can see a picture of microsurfacing being placed on the right. You can also combine all of these, for example, fog seal over a chip seal, or microsurfacing over a scrub seal, and any sort of combination of surface treatments is called a combination treatment, and those are very powerful possibilities. We then also have structural treatments. We have 3 different common structural treatments, including hot-in-place recycling, cold-in-place recycling, or full depth reclamation. These are HIR, CIR, and FDR. We can have cold central plant recycling, or CCPR. This is where we make an asphalt mixture at ambient temperature with 100% RAP and some ad rock if you would like, but using asphalt emulsion. We can have base treatments. This is either base stabilization or soil stabilization. And then finally we have pre-treatments such as prime coat and tack coat. So these are all the different types of treatments out there that we can use asphalt emulsion with. And many of these treatments, such as CCPR and the base treatments, full depth reclamation, cold-in-place recycling, those can use other stabilizing agents such as asphalt foam and Portland cement concrete, Portland cement or lime as stabilizing agents, but we're focusing here on asphalt emulsions. Now, if you want to find out more about asphalt emulsions or about these asphalt emulsion-based treatments, there are a ton of additional resources. If you search FHWA pavement preservation, you have free guides, technical documents, trainings, and checklists available. Lots of good information there. There's a fantastic transportation research circular, which is also free. It's called Asphalt Emulsion Technology, or E-C102. If you search Asphalt Emulsion Technology, TRC, you will find it with no problem. An excellent, excellent document. There are also many very nice industry resources. For example, roadresource.org is a cornucopia of resources. It's an encyclopedia of all things asphalt emulsion base. Very, very nice resource. And then ERA, EMA, and Slurry, or ISA, ERA, Asphalt Reclaiming and Recycling Association, ISA, the International Slurry Surfacing Association, which is slurry.org, and EMA, the Asphalt Emulsion Manufacturing Association, or EMA.org. All of those also have guidelines and technical documents available. And then finally, my old standby NCHRP reports. These are also online for free. You do need to enter your email address, but I have never received spam from NCHRP. They're excellent, excellent, excellent resources. And this is kind of a bracket. One of the first ones was NCHRP Report 523, which is the optimal timing of pavement preventive maintenance treatment applications. Very nice document. And then most recently, actually an FHWA document, also available for free, using reclaimed asphalt pavement and pavement preservation treatments. I recommend you start with these two, but then take a look at that FHWA document. Specifically look at the references, because there are probably 6 to 8 free online NCHRP/FHWA reports, and they're all fantastic. I just didn't want to list them all here, but they're all within the references of the FHWA document or documents within the references of the FHWA document. And then a small little plug here. These are not free. There is a charge associated, but the University of Arkansas has 4 online certificates: an introduction, an application, a manufacture, and a quality of asphalt emulsion. And if you search asphalt emulsion UARK, University of Arkansas, you'll be able to find out about those certificates and how to register for them. So that's a brief overview of emulsions. I just wanted to make sure if you didn't know what emulsions were, you have a little foundational knowledge, because when we specifically talk about high float emulsions, we're going to talk about a very, very unique subset of asphalt emulsions in general. So let's start with some patents. And this is kind of fun to search through old packets. There's a lot of information in there. Some of it's a little cryptic, but you can find a lot by looking at patents. And all these are available online for free as well. So U.S. patent 2,855,319 talks about a new asphalt emulsion that mixes aggregates with asphalt emulsion. And the goal is to increase the temperature range, specifically increasing the high temperature hardness without affecting low temperatures. So that second sub-bullet there is the first main takeaway of high float emulsions. We're really only talking about modifying the high temperature performance, not the low temperature performance. And the solution in this patent was a tall oil binder additive that you can either put into the asphalt binder before making the emulsion, or you can put it in the soap solution when you make the asphalt emulsion. So that is the first patent. The second patent, I'm just going to call this 4.4 million and change. This is where they introduce high float emulsions using a spray seal coat, also and more commonly known as a chip seal outside of the wonderful state of Texas. And they talk about having a rapid setting asphalt emulsion. And this is a black liquor soap skimming, or a tall oil, or a pitch, or a derivative, or a combination binder additive. And this is where patents get a little wishy-washy. Usually they're dealing with proprietary information, so they don't want to give away exactly what they're putting in. So they have kind of these ubiquitous catch-all categories, such as black liquor soap skimming, or tall oils, or a pitch, or some sort of derivative. But the point is it's create a rapid setting asphalt emulsion. And this is in contrast to the 2.8 million patent above, which was a mix. So it was a slower set. It was probably either a medium or it was probably a medium set emulsion. It may have been a slow set emulsion. But this new one, the 4.4 million, is a rapid set. And you can either put the additive into the asphalt binder or you can add it to the soap. And then finally, 4.6 million. This is just for a chip seal. This is explicitly rapid setting as well. And it's resistant to rain and wear. It has increased durability. It has reduced high temperature flow. Notice how they emphasize the high temperature. And then it provides improved strength and toughness. Now my friend and colleague Arliss will enjoy listening to me try and stumble over some of these words. But for patent 4.6 million in the soap solution, you had a tall oil alkali metal hydroxide, which is a base. That was pretty good. And then you can also have a carboxylic acid ester added to the binder, or a soap solution, or in the emulsion itself. So again, some sort of additive that's either put into the soap, or the binder, or the emulsion after it's fabricated. So these are this is kind of a history, the leading up to the development of, and then how we started using high float emulsions more frequently. And this really all started in the 50s and the 60s. And again, in the beginning, we wanted to increase the high temperature hardness without affecting low temperatures. We wanted to use it in a mix form at the beginning, and we wanted this mix of emulsion and aggregate to be resistant to water. However, in the 80s, we moved on and we kind of transitioned more into rapid setting, and this is for seal coats or chip seals. And lots of the same benefits as before, that high temperature hardness without affecting the low temperature. We want it to be resistant to water. And here we wanted increased durability, strength, and toughness. And then today in the 2020s, really a lot of the focus is around this concept of a gel-like structure, and we'll see why I say that moving forward. There's been some research recently that's talked about this gel-like structure. And in mix applications, we want to increase the strength and stability. And in spray applications, we want to increase chip retention, and we want to allow for dense aggregates. So chip seals usually are single size, low fines aggregate, but high float asphalt emulsions allow for a denser grade, a little dirtier aggregate, as we'll see coming up. Now, if you want a nice summary of where high floats can be used, I encourage you to take a gander at AASHTO R5. And you can see these are the different treatments that high float asphalt emulsions can be used in. We got the dense graded up top. We got a layer of surface treatments, and then some pre-application treatments as well. So a HFRS, a high float anionic rapid set high viscosity, can be used in a chip seal, sand seal, sandwich seal, or fog seal. And HFMS-1, a high float anionic medium set low viscosity, can be used in a sand seal, fog seal, and tack coat. And HMS2, I forgot the F there, I apologize. And HFMS-2 can be used in a fog seal or prime coat. And HFMS-2S, so that has a solvent in it, can be used in dense graded, slurry seals, fog seals, and crack filler. And then finally the CHFRS, this can be a -2HP, a -2P, or a -2SP, is a chip seal or a sandwich seal. So just mapping the different type of high float emulsions, and again that column in the middle, I apologize, that should read HFMS-2. So we got the 5 emulsions across the top, and then the variety of treatments they can be used on along the side. Now, where are they used? This concept of dense graded stockpile mixes, because you get that good initial coating, you get retention of workability over time, so this is good for such applications such as patching during winters, resistance to stripping, and good resistance to rutting and shoving. With open graded mixes, these high floats give you good resistance to drain down. It helps prevent stripping, and it retards the closing of the voids. So one potential issue with open graded mixes is over time the voids kind of close up, and this is a little less likely with high float emulsions. We can also have dense graded seal coats, or those chip seals. This provides good wetting of the aggregate, which means that that aggregate wants to stick to the asphalt emulsion residue, which helps with aggregate retention. There's also resistance to bleeding, so that asphalt emulsion residue does not come up through the chips and then rise to the surface. And it also allows for softer residues, which is good for cold climates. And big surprise, two of the documents we're going to look at, one is from Alaska, one is from Minnesota, and I would classify both of those as cold climates, and they're both using high floats. And when I talked about this concept of dense graded seal coats versus traditional steel coats, usually dense graded, or usually chip seals have single size aggregates. It's usually 3/8 of an inch, can be a little bigger, can be a little smaller, but very little fines, but it's as single size as possible. But here you can see there's approximately 50% P4, which means that half of it is smaller than that typical single size chip, and you have quite a bit of 40, about 4% passes the 4, and about 4% passes the 200, so there's quite a bit more fines in there too than typical. And this allows for a more stable mix with high floats and less traffic dislodgement. Now, if you do use high float emulsions with the one-sized aggregate seal coat, so the more traditional 3/8 inch only aggregate size, you do get some better chip retention, you get better film strength at high temperatures, and resistance to shelling at low temperatures. At least that's the theory behind high floats. Now, TxDOT has a very nice document along with Alaska and Minnesota. TxDOT also uses a decent amount of high float asphalt emulsions. And so if you search properties and uses for high float emulsions, if you search that on the internet, you can find a very nice document from TxDOT, and it is free and online. A good summary of all the work that they've done over the years. So that's a brief introduction to high float emulsions. Now let's talk about the residue. A lot of conversations around high float talk about the residue, and specifically it's because one of the benefits of high float emulsions, according to the literature, is it has a gel-like residue structure. Now what on earth does that mean? Well, let's take a look at 2 tins of asphalt emulsion residue. 2 tins of material. On the left is straight asphalt binder, and then on the right is the high float rapid set residue that was manufactured based on the straight binder on the left. So the source binder is the same for both of these. On the left is just the binder before anything happened to it, before you made the emulsion. On the right, it's the same binder, but a high float asphalt emulsion was made with that binder. And you can see after 6 hours, there's no flow at ambient temperatures. So asphalt binder is a viscoelastic material. It will flow over time, even at ambient temperatures, because it has a viscous component to it. You can see that very clearly on the left. But on the right, the high float properties of the asphalt emulsion residue prevented that flowing from occurring over 6 hours at ambient temperatures. And you can see something similar here on the right. Another picture, same story. On the left is at 1 hour, on the right is at 8 hours, and then within each picture on the left is the high float rapid set residue, and in each picture on the right is the straight binder. So the same situation is on the left, but instead of looking at 6 hours, we're looking at 1 hour and we're looking at 8 hours, and you can see how that high float residue stays in the tin. It does not want to flow out. Now, how do we obtain this residue? This is actually a very interesting question for asphalt emulsions in general, but specifically for high floats, what did people do to obtain the residue? Well, you can put it in a hot oven at 163 degrees Celsius for 2 hours in a beaker and have nitrogen in there. You can do the stirred can method, which is either 100, or you start at 100 and you go to 163 degrees Celsius for 170 minutes in a 1 gallon can, again having nitrogen in the air. Or you can do a warm oven, which is 25 degrees Celsius to 60 degrees Celsius, 24 hours at each of those two temperatures on a silicone mat. So these are the three methods that were explored based on the literature that I reviewed. And in this method, 5 emulsions were looked at, including an HFRS-2P, and that HFRS-2P is labeled number 5. Now, why is that number 5 important? Well, if we took a look at one of the graphs in there, there really was nothing noticeable in this paper. There was no real difference between the 5 different asphalt emulsions, except using the hot oven method, that 163 degrees Celsius, and then the size inclusion chromatograph. Another all the special chromatographs. Anyway, that long word that begins with C, that is the diagram on the right. And I understand as much about that test as I do about how to say the name, but it's my impression that what it does is it breaks material into molecular sizes. So you put your sample in this machine, and then over time you measure the molecular sizes using the RI response. You measure the molecular sizes over time, and as the specimen breaks down, you see different molecule sizes. And the interesting thing is this high float residue, number 5, is the one on the bottom. And you can see it is significantly shifted down from the other 4. Now, like I said, I'm not sure what this means. I really don't understand the test. I apologize. But obviously something different happened at high temperature in this test with the high float emulsions, and it happened on a molecular level. So I think this is something that is of interest. I would be very fascinated to learn more about it. If you want to learn more about it, here is the author and the title: Comparative Study of Recovered Binder Properties Using 3 Asphalt Emulsion Recovery Methods. It's from 2010, so it's an oldie but a goodie, and it's from the Journal of Testing and Evaluation. So I encourage you to take a look at that. There's a lot of good information in that paper. Now, another study I looked at was the Universal Simple Aging Test, or USAT. This is a thin film, 60 degrees Celsius or 140 F for 6 hours, and then you put it in a PAV, a pressure aging vessel for long-term aging. And this study looked at an unaged materials, 1 CRS and 3 HFRSs, and it looked at a PAV aging for 2 CRSs and 2 HFRSs. And it looked at the low temperature for all of the residues. So you can see here, this is the stiffness at 60 seconds. And specifically, I'd like you to take a look at these 4 different binders. You can see overall, the polymer modification does soften it, especially for the high floats a little bit. And all of the other 3, the CRS2, CRS-2P, and the HFRS-2 had similar stiffness and relaxation rates, except for the polymer modified high float, which was interesting. So there's some sort of interaction going on between having it being a high float and having a polymer modified. And now this is at low temperature. Remember, I talked quite a bit about how, in theory, high float shouldn't impact low temperature performance. It only impacts the high temperature. But here we may be seeing something a little different, and that's definitely something worth looking into. And this can be helpful for the traditional chip seals in low temperature environments, keeping that aggregate retention, especially with snowplow damage. You can read more about this. This can be found free online. The Emulsions, Recovery, Aging, and Rheological Testing. This is an FHWA technical white paper. So if you search that long, series of letters and numbers, you should be able to find that article online. Now, another paper looked at two different recovery methods. It looked at distillation, 204 degrees Celsius for 1 hour, and thin film, 60 degrees Celsius for 6 hours. And the second one is now AASHTO R78 Procedure B. It looked at dynamic material functions, G omega and tan delta omega. They found that the CQS residue is similar to high float residue at intermediate low temperatures, but at high temperatures, high float residue was less dependent on the frequency than the CQS residue. So this is kind of going back to the standard discussion about how high float emulsions really don't impact intermediate and low temperature properties, at least not as much as they potentially impact the higher temperature testing. And they felt that the reason behind this is standard asphalt emulsion residue is Newtonian. They felt that high float residue did not behave in a Newtonian fashion. It was something intermediate between a Newtonian and a Hookean behavior. They also ran MSCR, the multiple stress creep and recovery or massacre test, and they found that the high float residue had an improved resistance to deformation versus the CQS. So again, this is these high float or high temperature properties. And they found at a steady shear viscosity, the gel structure they observed was destroyed at higher shear rates. This is just a very high-level overview of the paper that I reviewed. There's a lot more information by Jasso and Lambden. The rheology of asphalt emulsion residues obtained by different evaporation methods, and this can be found by our friends up north, the Canadian Technical Asphalt Association, and this is published in 2023. Now, for emulsion characteristics, we're going to finish up with Justin Suda. He has published two very, very interesting papers on rheology and microstructure of high float asphalt emulsions. He found that high float asphalt emulsion residue is not an elastic solid, it's not a viscous fluid, it is not a Kelvin-Voigt solid, and it is not a Maxwell fluid. Now, if you want to learn more about these, please take a look at my viscosity Pavinar, because asphalt binder is considered a combination of all of these. But Justin found out that when you have a high float residue, you move away from these kind of traditional definitions of asphalt binder or asphalt emulsion residues. He believes that high float asphalt emulsion residue is completely different than the original asphalt binder. And one of the ways that he found is it does possess a yield stress, about 22 pascals, and he feels that this yield stress can help prevent bleeding. He also looked at the microstructure. He found that droplets do not coalesce, they coagulate. This goes back to that gel-shaped structure, and that's because the droplets retain their individual spherical shape. And he believes this could be potentially because it traps a little bit of water. So this can be found in high float emulsion residue, its unique rheology and microstructure, and this again is from the Canadian Technical Asphalt Association, this one from 2016. And Justin continued on and looked at some methods and metrics to try and quantify the high float residue behavior. And he ran a whole bunch of old school tests, including penetration, viscosity, and the float test. But then he also ran some newer tests. Now, I'd probably get points off because you probably cannot read those axes because it's a kind of a bad scan of the article that I received. However, you can't put your own labels on now, and now at least the labels are readable. The numbers may still be a little grayed out. But you can see here that Justin developed a DSR flow curve test, and this looks at the apparent viscosity versus stress. And essentially what we're looking for is that as the shear rate increases, the flow tends to decrease. And high float residues offered similar yield stress during the different ramp rates. So it's kind of interesting. He looked at a whole bunch of different asphalt emulsion residues. This specific graph is of a high float, and that apparent viscosity is relatively flat, and the other ones had much different shapes. And if you want to learn more about that, high float emulsion residues, suitable methods and metrics for testing viscoelastic materials, again, in CTAA from 2021. So that's a nice overview of high float residue. Now we're going to go a little more into some other research that moved just beyond the residue, but kind of looked at some different both lab and field applications. So we had a very nice study that looked at the lab performance of chip seal. So they looked at 3 aggregate blends, 4 emulsions, 3 emulsion application rates. All of those should be familiar except for the third one. That's a CRS-2TR. That is not a typing error on my part. It has tire rubber in it instead of traditional polymer, so they called that TR. They ran the sweep tests, the ASTM D7000. They looked at the DSR for some rheological characterization, and they looked at FTIR and SARA analysis. For their high float findings, they found that the high float, which is the one on the far right there, had the highest aggregate retention. So good job, high float. That shows that it could potentially retain those chips better. At high temperature, it had the highest G star and the lowest delta. At low temperature, it had lower S values and the same M values. So again, impacting that high temperature a little more than the low temperature. And it had the lowest carbonyl indices and the lowest asphaltene growth as well, which means it was not oxidizing and it was staying, it was not stiffening as much as the other asphalt emulsion residues. Their final statement was high float provided adequate performance, and you can find out more about this in the Transportation Research Record journal publication cited there below. Another group looked at dense graded high float surface treatments, and these were chip seals with either HFMS-2 or HFMS-2S, and they used dense graded aggregate. So I'd mentioned before that usually chip seals have the majority of materials on that 3/8 inch sieve, very little on the P200, but you can see here there's a little bit more distribution, especially in the number 4 and the number 8 sieves, and then a little bit more dust there on the number 200 sieve. You can see the emulsion application rate is much higher. It's 0.75 gallons per square yard. Typically surface treatments place between about 0.4 and 0.5, so this is quite a bit more emulsion. It's also quite a bit more aggregate at 75 pounds per square yard. And the objective of this research was to find the optimal application rate of the emulsion and the aggregate. The authors here talked about how historically this has just kind of been, you go out in the field, you play around with it, and you settle into something. Lots of just eyeing it, taking a look at how it's behaving. They wanted to design a mixed design method, and so they did. They designed a 5-step mixed design method that was developed to reduce flushing and bleeding, to reduce raveling, and to reduce potholing. And they also developed a new test for compacted density, which is pretty nice. The work that they did, this is back in the early 2000s, they felt that this mixed design was step 1 and it needed to be validated with field work. So you can find a very nice Alaska DOT publication on this if you search FHWA AKRD0503, that number there below. You can find that online free of charge, and if you want a little more synthesized version of that report, take a look at TRR. In 2007, McCaddy put a Transportation Research Record out on this as well. Another piece of research looked at thin maintenance surface treatments, a single and a double chip versus a slurry versus a micro versus a cape seal versus a thin lift overlay. And the single and double chip did include a HFRS-2P. This study captured PCI and skid resistance in the field, and I really want to emphasize this. This paper explicitly said for all sections, proper material and quality construction is key. And I hear a lot of people rolling their eyes, a lot of people's heads are falling on the table because they're falling asleep, because people hear this time and time again. But it is important. There's a reason that it is said time and time again. And that is because if you do not have proper materials and you do not have proper construction, you will not have good performing pavement sections. Now you can see here with the PCI, the high float, does pretty well. That single chip seal and the double chip seal, that's all kind of up in that large area that is shown up in top. So they really didn't see any significant disadvantages to using high float versus the standard CRS-2P. And in fact, they said that all high float rapid set -2P sections had good performance. And you can find this in a Iowa State University article, Thin Maintenance Surfaces Phase 2 report. And they also had a follow-up in Transportation Research Record. And if you can also find they have a Phase 1 report, lots of good information in there as well. So some good work there done up in Iowa. This study looked at high float as a tack coat. They looked at 4 different tack coat materials. One of them was a high float, that HF right there. They looked at 5 different application rates, 3 different curing times, 4 curing temperatures, 3 surface textures, and they used 2 different overlay mixes. And they found that the SS-1VH tack coat was the best performing in the tack coat shear device. But you can also see here with this graph that in general, high float was approximately the same as some of those more traditional tack coat materials. It's more similar to the standard slow set and the asphalt binder tack coat. But that very hard no tack showed the best performance in the tack coat shear device. And you can find out more from the Illinois Center for Transportation, ICT R27-100. They put out the best practices for implementation of tack coat Part 1 laboratory study in July 2012. Now moving over to mixtures, there was some work done with cold in place recycling and high float. They used the semicircular bend, 4 different stabilizing materials over 3 labs. They looked at engineering emulsion, they looked at HFMS-2S, and they looked at traditional CSS-1 with cement, and they also looked at foamed asphalt. And they measured the low temperature fracture energy, which they called 5. And they recommended a minimum 5 value of 230 joules per meter squared. So basically, what is the minimum fracture energy required for a good performing mixture? And you can see that the high float performed higher than that 230 in all of them. So the high float passed, the engineering emulsion passed, and the foamed passed. The CSS-1 with the cement, unfortunately, did not pass. But you can find out more about this, also free online, in optimizing cold in-place recycling applications through fracture energy performance testing. This is an LRB report, Minnesota/RC 2016-21, and this is put out in 2016. So I know we're getting a little long here. We're almost at 38 minutes. We're at 38 minutes right now. But I do want to cover the 2 most recent reports with asphalt emulsion and asphalt emulsion residue. The first is NCHRP report 837. This is the EPG, the emulsion performance grade. In their survey, they found that these high float emulsions were all used, but by less than 10% of survey respondents. So high floats are not being used as much as those other emulsions for chip seals. They found that they looked at 1 HFRS-2P and 2 HFRS-2s in Phase 1. They did not use any high float in Phase 2, and Phase 2 is where they developed recommendations for both chip seal and microsurfacing specifications. So none of their recommendations actually had high floats used in them. They did include AASHTO T50. This was retained from the existing emulsion tests, so their proposed specifications do include AASHTO T50 if you're using high float, and that's just the traditional float test. If you look at AASHTO T50, it essentially just says follow AASHTO ASTM D139. But there were kind of some oddities here. First of all, they did put the float test under the original emulsion testing, but it was the original emulsion residue section, not the emulsion itself section. So I'm wondering if when they say original emulsion, do they mean both emulsion and not aged residue? I'm not 100% sure, but there's a little bit of oddity going on there. And I do want to notice that ASTM D139 does not explicitly recommend 60 degrees Celsius. In fact, it goes out of its way not to mention a recommended temperature. That 60 degrees Celsius is from M140, M208, and M316. So if you just search NCHRP report 837, you'll find this. It's the performance-related specification for emulsified asphaltic binders used in preservation surface treatments. And that was put out in 2017 by NC State. Texas A&M has also done a lot of great work through the Texas Transportation Institute. I'm going to explicitly look at two different references. You can see the alphabet soup of the two references up there. If you search either one of those, you will be able to find both of them online. But that -23, Texas -23, indicates that that's a 2023 article. There's a lot of articles in between there. So they've done a tremendous amount of work to develop these hot applied and asphalt emulsion residue standards. And the high float residue follows all of this, except for the residue properties. You can see here that for the two high float emulsions that they look at, the HFRS-2 and the CHFRS-2, they meet the specified SPG grade, except the max phase angle is 84. So if you look on the left, you can see phase angle delta max at temperature, where G star sine delta equals 0.65 kilopascals. It's the second to last row of temperatures. You can see there's a 67 above it, and then it says 80 for the phase angle. That is an 84 for these three emulsions. And then they also have the float test as part of the requirements. So high floats are treated the same as the standard, except all the emulsion residues are a maximum phase angle of 84, not 80. And then also in 2022, they do have a special provision to item 300. They include having T50, Astro T50, being greater than 1200 seconds at 60 degrees. But if it's less than 1200, using the R78 procedure B, that low temperature evaporation study, you need to rerun the flow test using the T59 residue recovery. So get that stiffer binder, because the distillation is a lot higher. It's a much higher temperature. It's a much more aggressive way to drive out the water and oil. Now, as I mentioned, they did have several reports between 2001 and 2022. I bracketed it, though, because the 2022 had the final implementation for the specification, but the 2001 was the only one that actually had any data on high float. So there's a lot of good information on the ones in between, but high float kind of gets lost in the shuffle. One of the reasons is because they found out that high floats were relatively uncommon, and performance of high floats was not governed by low temperature properties. So this kind of goes back to, they saw the biggest differences at the higher temperatures, but not at those lower temperatures. And in a 2001 survey, 76% of the TxDOT districts said that they were either familiar with or using high floats, whereas 66% of industry and academia were. But you can see that HF, the high floats, performed fair overall. And this is versus good or versus poor. So it's good, fair, or poor, and overall they've dictated that the high float emulsions performed fair. So that is the summary of the high float emulsions. We gave a brief overview of asphalt emulsions. We talked about high float emulsions in general. We talked about their residue, and then we went into a little bit of research. So we're at 44 minutes. This went long, but thank you very much for joining me, and I hope you have an absolutely wonderful day.